Hi, welcome to a new session of electrical machines. In today's class 2, we are going to see the problems based on EMF equation. In the last class, we have derived the EMF equation of a single phase transformer when an input voltage of sinusoidal is given as input to a transformer winding on the primary side. The EMF induced on the primary is given by 4.44 N1F multiplied with the maximum flux. The maximum flux also can be replaced in terms of its maximum flux density multiplied with the area of the cross section, and with the mutual inductance E2 is also obtained as 4.44 N2 F multiplied with the maximum flux. So this derivation we have done in class 1. Let us see, based upon the EMF equation, how the questions are framed. In the question 1, you can see a 20 kilovolt amperes 4400 by 440 volts 50 hertz single phase transformer has an EMF per turn as 11 volts. We need to calculate the number of primary and secondary turns, and if the flux density is 4 Tesla, then calculate the net cross sectional area of the core. So for the solution, first you calculate the data which is given from the problem. E1 or V1 it is given as 4400 volts, and E2 or V2 is given as 440 volts respectively. Then EMF per turn is 11 volts, and the maximum flux density is given as 4 Tesla. With frequency 50 Hertz, we can calculate the number of primary turns which is given by E1 by EMF per turn. So the value obtained to be 400 turns for N1. Similarly, we can get the value of N2 which is 40. So clearly it's a step down transformer. Now the net cross sectional area is given by A is equal to the maximum flux by the maximum flux density. So to calculate the maximum flux, we have the formula EMF per turn by 4.44 multiplied with F. So with this we get the value of maximum flux which is 0.0495 Webers, or the area of the cross section which can be obtained from the maximum flux by its density, it is obtained to be 0.012 meter square. You can change it to centimeters also. Now in the second problem, a single phase transformer has 220 primary 660 secondary turns. The net cross sectional area is 100 centimeters square, and if the primary winding is connected to 50 hertz supply at 440 volts, then we need to calculate the maximum flux density as well as the voltage induced in the secondary winding. So with the same formula and the data which is given in the problem, the input voltage is 440. We need to calculate the output voltage. N1 is given as 220, N2 is given as 660. With frequency 50 hertz, the area is changed from 100 centimeters to 0.01 meters. And now the maximum flux is calculated here, which is obtained to be 9.009 milliwebers, or you can take roughly 9 milliwebers. The maximum value or the peak value of the flux density is given by the maximum flux divided by its area. So area it is given to be 0.01. So we'll get the value of maximum flux density which is 0.9 Tesla. Similarly, the secondary induced voltage with the formula of turns ratio E2 is obtained to be 1320 volts. So this is how the problems are framed based upon the EMF equations. We can go in with another example where we have a single phase 250 kVA 6600 by 400 volts 50 watt transformer with 280 secondary turns. We need to calculate the approximate values of primary and secondary currents. Then we need to calculate the number of primary turns, and also we need to calculate the maximum value of the flux. So as I told you, you need to take the data from the given problem, and here a special mention, 250 kilovolt amperes the power rating is given. So this is helpful to calculate the value of current, where the formula for power is P is equal to V into I. Therefore I is equal to P by V. So I1 it is given by rated kVA into 1000 by V1, which is nothing but here it is obtained to be 37.87 amperes, and I2 which is obtained to be 625 amperes. Now here primary current is lesser than the secondary current, because it is understood that the primary voltage is greater than the secondary voltage, and from the turns ratio these currents which we got, we can estimate that these are the approximate values of the currents. Fine. The number of primary turns can be given from turns ratio N1 is equal to N2 multiplied with E1 by E2, which is obtained to be 4620. Now you can see N1 is again greater than N2. So as I told you, it's a step down transformer. Now to calculate the maximum flux, we have the formula E1 by 4.44 multiplied with F and multiplied with N. So with this, the value is obtained to be 6.43 milliwebers. So this is how the questions are framed under the same equation, EMF equation of the transformer. So for the practice session, I have identified a question 4, 5 and 6 with the answers given for the given problem. So you can cross check the result and comment in the chat box whether you got the same answer or not, and whether you are able to solve the transformer problems or not, you can comment in the chat session. So that's all for today's class. I hope you like this session. Please share among your friends, subscribe to this channel and press the bell icon for the future notifications. Thank you.